Well, it's time. Welcome back, everyone. We're about to finish off the second week so far. And the other big announcement that we have at the moment is week 4 is coming up pretty fast. And week 4 is going to be our first exam that we're going to be getting through. Before we even get into the third week, next week, you'll see on the Canvas page, I'll have information posted here for the definite and exact coverage on what's on the first exam, as well as associated review exam 1 questions that you can take a look into for extra practice. As far as the exam writing goes, I'm not going to try to write an exam that is fully 75 minutes long, in the sense that you're going to be writing the whole time from start to finish with your hand getting tired at the very end. I'm going to try to make it around the range of, say, about 60 minutes, giving you enough time to carefully consider each problem, double check your work, and spend the additional 15 minutes to just finalize any answers and those kinds of things. As far as writing goes, also I try to keep them pretty parallel to what we did in class. The lecture notes themselves are a pretty good review on what could be on the exam. And same with the homework assignments. The homework assignments, which are based on the lecture notes, on their own are going to be a great review for their first exam. And that'll be true for all exams, including the final. But I'll definitely post additional exercises as well, just to give you some new, fresh problems to take a look into. Well, any questions at the moment, folks, with the exam 1 or otherwise? So if you ask, are you going to send the exams to each Tennessee Center and Pocatello and Idaho Falls? Yeah, absolutely. I emailed everyone in the class on your preferred location, so whichever campus you're closer to. And I have just about a complete set of responses. If you haven't said what your preferred location is, don't hesitate to email me at any point. I'll get that marked down. Then when we get into week 3, probably the very first thing I'm going to do on Monday is directly email everyone in the class just to double check I have it recorded right. So if you said you were going to test in the Pocatello Testing Center, I'll be sending you the instructions for scheduling your exam on the following week, week 4 for exam 1. If you said the Idaho Falls Testing Center, I'll send you those instructions. And if you're registered for the in-person section, there's 4 of us total, 1 of us in the classroom right now. Then the expectation is that you'll test in this room. But as I email everyone in the class, that'll be our opportunity to double check things and see how it goes. I try to get those instructions out really early because various testing centers, say like the Pocatello Testing Center and the IF Testing Center, do not like to schedule the exams on the same day. So I'm always going to try to be on the ball, sending out the instructions at least a week early. Other questions at the moment? Okay, well, pretty much we're working through the material. We had kind of a rough start with the sudden cancellation of class on Thursday. Sorry about that. And I also even sent out a different announcement to everyone about potentially a problem getting class set up on Thursday. On the actual classroom I'm doing this all from, the schedule says that there is a Chemistry 2 class that goes from something like 11 a.m. to 12:50 p.m. I wasn't sure how I was going to get everything set up in 10 minutes, but no one showed up. So I guess they moved them out of this classroom. So we won't have any issues getting started on Tuesday or Thursday. So far, we're getting through section 2.3. We're about halfway through the content. Section 2.3 is really pretty interesting because the material we get through here actually connects back when we're in chapter 3 on logic. Logic is concerned with operators such as not, and or. The corresponding things are going to be the complement, intersection, and union. So that's what we're about to take a look into to start off 2.3. Well, any last questions, folks, before we begin our work today? Okay, let's jump in and get started. Here's the problem we left off on our Tuesday's class. There's a lot of different set operations and really fast examples down below. In the space we provided, we can solve these pretty quickly. And I made the sets that we're concerned with pretty simple. They're the same on each example, so that we're going to focus mostly on the essence of each of these problems, not on the sets getting messy. So starting off with the very first one, the complement of a set. Let's view this in terms of the set abstraction definition that we looked into last class as well. The complement of a set with respect to a universe, set A, is written this way, a little tilde symbol right in front of A. Some textbooks go with A bar, and we mentioned there's a lot of notations for this. It's not standardized. Depends on which subfield of mathematics you might be working in. What the complement, I'll write it this way typically, tilde A, becomes is the set of all elements in the universe that are not in the set A. So some people like the definition just in pure words. Other people prefer to see the definition in this method of writing it out, just using the set abstraction format. The complement of the set A is all elements X in a universe, such that is what the colon reads as, X itself is not an element of A. So comparing that with set abstraction, let me hide that for the moment. This is the universe, so this is where the elements are going to come from. This is the predicate function that we're concerned with, the condition that gets us inside the set in the first place. And that's essentially what we were practicing on definition 220. A set A will be the set of all elements in some universe such that some condition holds. This is just some brand new condition. X is not an element of the set A itself. So looking into our set A, it contains elements 1 and 5. To get inside the complement of the set A, you have to look into all the elements in the universe U that is not in the set A. So in other sense, just delete those two elements in A, 1 and 5, and then the complement of A becomes 2, 3, and 4. So that's our first run at the set operations. Any questions viewing it this way? Okay, these problems again, they go pretty fast. The major thing that we're spending time on is just understanding the definition verbally, understanding it in ordinary mathematical notation, set abstraction. Yeah, another great way to understand these kind of definitions is, say, through a Venn diagram, just seeing this visually. So if you're a fan of internalizing this kind of information this way, I stole this directly out of the textbook. Let's fill these out as we go, just to give another view of what we just computed right above. So if our set A contains elements 1, 5, and the universe is 1, 2, 3, 4, 5, essentially everything inside that box, that means 2, 3, and 4 are the elements that would belong to this set A. So all the elements inside the universe, not in the set A. Well, we're on our way. This is pretty much how most of these operations are going to go. Next one is going to be union. Then we'll look into intersection and set difference. Any questions so far on our first one? Okay, yeah, go ahead, sorry.
I was wondering if you mind if we use A bar or just the one that you've been using, or if you deduct any points for that.
I would not, yeah. If you used A bar, that's going to be totally okay with me. So yeah, I'd say pick the notation that just feels the most sensible to you. Stick with it, be consistent, and I would never take off points for that. In
Okay,
fact, to go along with that comment, yeah, thanks for asking about that. If you wrote, hang on, forget that this has to get bumped up a little bit more. If you wrote it this way, this is the typical way the author will write it. The author mentions it's sometimes written this way, so that means it's fair game in this class. If you'd like to write it out that way, that would be great, especially if the author mentioned it as well. And another way that comes up often is this way, A with a superscript lowercase c to stand for the complement. Another way it's written in other textbooks, it's kind of annoying to have all these different ways to say the same thing, but an A prime is also pretty common notation for a complement as well. And as long as I know what you're referring to, I'd be completely fine with any notation. So I'll say here, any notation can be used on both homework and exams. Thanks for asking about that. Other questions so far? Okay, So set complement, for various reasons which are kind of hard to explain, have lots of different notations. This one's usually used in topology. I think this one comes up more often than not in a context of statistics. And this is kind of the odd one now. It just depends on the textbook you're reading. I've seen it in a couple textbooks. One thing that's kind of nice, however, there are symbols that are more standard. And the next definition, we're going to take the union of two sets. So this is an operation that requires more than one set, like the complement. The union symbol is denoted like this. And this one is standard. This is not the letter U, it's just that particular shape. A union B will be the set of all elements that are either in the set A or in the set B, or in both set A and B at the same time. So this OR is pretty special. A union B is trying to say your element came from A or it came from the set B. And notice when we write it down this way, using our set abstraction method, we just say OR once. That OR is really pretty special, and this is going to connect back to chapter 3. This is called an inclusive OR. An inclusive OR always means either one thing is true or the other thing is true, or both things are true at the same exact time. If we meant the exclusive OR, either A is true or B is true, but not both, we would have to mention that definitely. So this is always going to be our default way to think about the statement OR. So if we have sets 1, 5, 3, 5, 7, and all we're doing is taking the union now of those sets, it's pretty fast. We can write A union B. So there's our set operation is going to be the set of elements that are in both the sets A and B at the same time. So to get inside there, you're either in A or you're in B. So let me list the A elements, 1, 5. Let me list the B elements, 3, 5, 7. We have to be careful though, right? Sets only can count unique objects, and these are weird looking commas, by the way. I don't know why they got so strange looking. So we do have to write this in a simplified form. If you put 5 here, you would have to simplify this back down to the set 1, 5, 3, 7. So in other words, the set A union B, it has a definite amount of elements, no matter how you wrote it. Even if you duplicated 5, the cardinality of A union B in this problem has to be 4. So you might get a point off if we duplicate 5. If it's a 5-point problem, say on exam 1, you might lose a point. Just a quick reminder that the cardinality has to come out as 4 when we go to write out this union. So again, they go pretty fast. Main thing we're doing is just absorbing all this brand new terminology, unions, complements, and intersections. And if we want to see it as a Venn diagram, which is kind of a nice visual way to look at it, the shading in these Venn diagrams refer to the actual set that we're computing. So here the shading was for the complement of A. This one, the shading is going to be for the union. So if A contains the set, the elements, 1, I want to put 5 in a pretty interesting spot, right in the middle where they intersect, because that's a shared element. If B contains the elements 3, 5, 7, then A union B is just the collection of all of those elements together into one set. That overlap is interesting as well. That's going to be our next operation, the intersection. Any questions, folks, with that union symbol there, or this union problem here? Okay, let's try it out all over again. From union, the next interesting thing is, what if you wrote down a set just like this, but you flipped the word or into the statement and? That would mean you're just looking at the overlap. And if we're flipping from an or into an and, we take the union symbol and we just literally flip that as well. So that's kind of nice logically. Here's what it looks like. The intersection, actually let's leave this on the next page since this is taking up some room for the diagrams. The intersection of two sets A and B is denoted this way. A intersect B is how we would read that. If you see a symbol going this way, you're talking about intersection. And that means in the definition of the set, our difference is we put an and here as opposed to the or. It will be the set of all elements that are in both the sets A and the set B at the same exact time. We can see it visually right here. It's the 5. So computing A intersect B, it's really fast on this one. A intersect B in this situation is just going to be 5 itself. Well, any questions, folks, with that fast operation here? Okay, and like we mentioned before, complement is the weird operation that has lots of different ways to indicate a set complement. But both union and intersection have very standard symbols. In just about any book you're going to take a look into, right where the red dot is, will always indicate intersect sets. In terms of the Venn diagram, we can see it right here, but just for the sake of parallelism, let's go to the next one just to complete the order we're doing these. A intersect B only has the overlap shaded. So if we listed out the elements of these sets, A contains 1 and 5, B contained 3, 5 already there, and 7. That's where the intersect will be, just the shaded part. Well, we're getting through these kind of quick. The next one is going to be set difference. Let me hide a little bit of that so it's not a distraction. Set difference also has and included, but notice we say X is an element of A, and at the same time, X is not an element of B whenever we're doing the set difference, A minus B. One way to think about it is when we write the set difference A minus B, we're taking all the elements contained in the set A, but deleting the overlap, remove any set element that's in both A and B at the same time. So we'll indicate difference in this way. A subtraction, we're not doing a mathematical subtraction arithmetic, so this has a highly precise, different kind of meaning. And it just means we're doing this particular operation. The big part of what's going on with this is we're not allowing X to be in the set B whatsoever. If we say A set minus B, let's highlight B as well, just to convey that. So if A is a set 1, 5, B is a set 3, 5, 7, notice that in the set B, 5 occurs in A, so we just delete that when we do the set difference. A minus B, we're not concerned about the elements 3 and 7. They're not in A in the first place. We're just concerned about the elements that are in B. We take them out, so take out the 5, and all we get is 1 itself. I think out of all of them, this one's kind of the harder one to visualize. So this is where the Venn diagrams shine. Let's grab this. Well, there's 2 of them here. Let me grab just the one that's relevant to our problem, A set minus B. So if A is 1, 5, just like before, and B is 3, 7, A set minus B means we're eliminating anything that belongs to the set B and just writing what the remainder is. Looks like a weird kind of moon there. That's what's going to end up in A set minus B. So that's the fast run through of all of our set operations. Any questions or comments so far at the moment? Okay, so they're pretty fun operations. We'll be turning back to these again once we're looking into logic to see what the tie-in is for these kinds of symbols. For the moment, think of intersection as representing and think of union as a representing an or. And the last one, think of complement as representing the way of saying not as self, just like we're saying X is not an A. So we'll loop back on those in chapter 3 on our discussions on logic. But for the moment, the next thing we're going to take a look into is set equality and subset relations. So let's take a look into that next set of content. To me, this is where this stuff kind of gets a little bit trickier and vague, not for set equality, but subset relations, an element of a set relationships turned out to be kind of tricky. This is a great question that was asked last class when we looked into the statement X is an element of A. A great question was, what can happen for looking into a set kind of like this one? And we ask, is 1 inside the set A? It is not. The elements of the set A go A, B, an entirely new set, 1, 2, 3. So 1 itself is not an element of that set. This becomes pretty tricky when we look at that operation, element of, together with the subset relation. We'll have to work really hard to keep those two things separate in our minds. So we'll use some analogies as well to help us out. But first, let's start tracking through the definitions. This one's not too bad to get through. We kind of have used set equality a little bit before informally, even before we defined this. We'll say two sets, A and B, are equal, writing it out this way, A equals B, if A and B have exactly the same elements. So for a really quick example, if we write down A goes 4, 12, 13, just a random set there. B is a set, 13, 4, 12. And if C is the set, 1, 8, then we can say immediately that we have A is equal to B. It looks funny, but recall when we write down a set, order is unimportant. If order is important when we're writing down these elements, we're talking about a sequence rather than a set. And that'll be the starter for the next section, 2.4. So we look at the elements in set A, they're exactly the same elements in the set B. So we can write out directly A equals B. Now, certainly this one's the odd one out. C equals 1, 8 has nothing in common with either one of these sets. So we would say A is not equals, borrowing what we might have said in arithmetic or algebra, to the set C. Likewise, B is not equal to the set C. So set equality is kind of nice and straightforward. Just watch out for order and duplicate elements because that won't affect set equality. The next definitions are about subset relationships. But any questions or comments so far with set equality? Okay, let's look at these really carefully. There's some weird work we're going to be doing in example 9 and the next one, the challenge example that we kind of hinted at last class down here, example 11. When it comes to these relationships, there's two different ways to indicate a subset. You could use a symbol like that with a little bar, which essentially says we have a subset, A is a subset of B, or it's equal to B, kind of like a less than or equal symbol. Then we also have a proper subset definition. We'll say A is a proper subset of B, written out this way, if we're excluding set equality. But in either case, the subset relationship will say A is a subset of B if every element in the set A is also at the same time an element of the set B. So that's what allows us to have the subset relationship. This is kind of the more default symbol that's used in most cases in a math textbook, subset equals. It allows for the possibility that every element X and A is inside B, but A is also equal to the set B at the same exact time. So every element in the set B turns out also to be in the set A. But if we want to make a distinction that the sets cannot ever be equal, we'll use the proper subset relationship. So A will be a subset of B if this is true, but A itself is not equal to B. Well, coming down, here's some quick problems to practice this relationship. I have two sets, A and B, and a third set, which is going to be the universe, where all sets and subsets come from. Just the integers 1, 2, 3, 4, 5, and so on, up to 9. And the first question we'll look into is A subset equal to B true? Well, A has the elements 1, 2, 3. B also has elements 1, 2, 3. But there's a problem here. There's an element 0 that belongs to A. 0 does not belong to B, so this relationship fails. A is a subset of B, or equal to B, if every element of X is also an element of B. 0 doesn't work, so we get to say on this one, A subset equals B is false. You might have said this entire statement so far in a different way. If you just said A subset equals B, like this, you're conveying A being a subset of B is false, and it's fine to write it either way. We'll say it's false because 0 is an element of A, and 0 is not an element of B. We have an element that does not belong to the set. So in other words, the set A is not fully contained in the set B. For looking in terms of Venn diagrams, there's a part of A outside of B, so they're not subset. It's not a subset of B itself. Well, that's one down. We'll take a look into a couple more trickier ones. Any questions at the moment? Okay, this one is asking if A intersect B is a proper subset of B. So that means we're thinking this relationship as a proper subset. Maybe the first thing we should do when we go to compute this is just compute the A intersect B, find out what the intersection is. So we'll start by taking A intersect B. A contains elements 1, 2, 3, and 0. 0 is not inside here, but recall A intersect B just contains the overlap, all elements that are common to both sets A and B at the same time. So the elements in common are 1, 2, 3. This set 1, 2, 3 itself is not equal to B. So that means that condition holds. A intersect B is what goes in this position right here, is not equal to B. Every element in A intersect B is definitely inside of B. To be an intersection, you had to be both inside of the set A and inside the set B at the same time. So that means this is a proper subset. Our final answer to this might be, therefore, A intersect B is absolutely a proper subset of B itself. Well, that's 2 down so far. Does that make sense on the ideas on what made this one true? Let me write out my answers in the same way. I said here, A subset B is false. Here, I want to write out A intersect B being a proper subset of B is true, just to be extra certain that we're conveying this in the right way, just matching up the way we wrote it in part A. If you left that off, I would assume what you're saying is this is a true statement. Well, any questions at the moment?
So, a proper subset means that there are things in common, but not necessarily everything.
Exactly, yeah. It has just this major part right here. To be a proper subset, those two sets in question cannot be equal. So that's why we looked into this part right here. Because the intersection of A and B is not directly equal to B, that makes this statement down below here true. Does that make sense with that question there?
Yeah, I think so.
Awesome. Well, here's where it gets a little bit trickier. This is a weird statement. First of all, recall that's the empty set symbol. So this is the set that contains nothing whatsoever. So my question is the empty set a proper subset of the set A? Let's think about that for a moment. This is kind of a weird statement when you really think about how are these things defined. To be a subset, every element of the first set on this one is the empty set, must also be an element of the second set. Or if we set it this way, the sets are also not equal at the same time for a proper subset, the way it's written down below here. So again, this one's kind of open to interpretation, but it does have one definite answer, which is a little bit weird. We'll expand on it in a moment. But any gut instincts or feelings folks have on this one? Would you all say that this is true or this is false? Keeping in mind, this is an extra tricky question. Yeah, good call. This is actually true. It's a weird kind of truth that we'll investigate when we're in chapter 3. This one is called true vacuously. That's kind of a weird statement when you say something is vacuous. That doesn't sound like a compliment, but in logic, it has a very, very precise meaning. The way these definitions work allow for a vacuous truth to occur, and it happens on this one, so good call. We'll say the empty set, subset of A, is true with a provision here vacuously. So let's expand on that a little bit. The reason we call this a vacuous truth on this one is because let's check on the condition to make this false. The only way we get a false statement is we find an element in the very first set that does not belong to the second set. That's the only way we get a false if we're talking about this subset. A false can also occur if the sets were equal at the same time if we're looking into the proper subset. But that's not relevant this time because the empty set is certainly not the same as the set A. A has stuff inside of it. It's not an empty set. So looking into this right here, we got a false because 0 was in the set A and not in the set B. And then expanding on vacuous truth here, the only way 0, excuse me, not 0, the empty set, subset A, is false is if an element X in the empty set is not in the set A. But we have an interesting problem here. That will never happen. We'll never get a false to occur because there is literally nothing in the first set, the empty set. So that's a pretty weird set we're taking a look into. Just highlighting that to convey when we got a false on part A. So to complete the thought, we'll say since the empty set, which can also be written this way, which looks more visual, has no elements, a false statement is impossible. So our statement here is MC set, subset of A, is true vacuously, just as a reiteration. So this is a pretty weird problem, but it's something we'll come back to. Vacuous truths come up a lot in some pretty weird contexts, and it comes up in mathematics quite often as well. In fact, this is pretty fundamental. If you've ever taken a probability class, you're defining a function, and this relationship has to work for the so-called probability set function to make any sense at all. We need that relationship to really work for us. Maybe just a couple more side thoughts. Here's where it gets a little bit strange. The empty set, being a proper subset of itself, is false. This is one of those nasty kind of gotcha questions that I don't like to write on exams. The only reason this is false is because we use the proper subset relationship, which says your two sets had to be unequal in the very first place. But the empty set is equal to the empty set, so this is a false statement. However, empty set, subset equals A, is always true. Doesn't matter what the set A happens to be. If you use subset equals like this statement here, this can never be false. Well, let's maybe put one more down just to convey that. The empty set, subset equals to itself, is in fact true. And this is the weird one out because of that exclusion, both sets being the same on the left and right-hand side. Well, there's lots going on with vacuous truth, like we mentioned before. We'll get back into those kind of topics in chapter 3. And like we mentioned, that's kind of what's going on in section 2.3. It's kind of a launching pad for discussions into logic, as well as just being extremely useful mathematically. Any last questions or thoughts, folks, on getting through these definitions? Okay, well, keep in mind also with the way these notes are being written out, they're pretty similar to the homework questions as well. But anything that's written in this orange or say a pencil tool like that is just meant to be an additional comment, not something you would have to reiterate and restate on every single one of your assignments. Next things we're going to take a look into are just a couple more applications to set theory itself. Disjointness will be an interesting topic to take a look into when sets don't overlap. It naturally leads into ideas of partitions, and then we'll end this section by looking into the definition of a power set before we go into the very next section 2.4. Well, here's another interesting piece of terminology with sets. Sometimes we don't want our sets to overlap. Sometimes sets are very interesting when there is nothing in common to both of them. And that when that occurs, we'll say that sets are disjoint. The full definition says, sets A and B are disjoint if there is no element X in a set A where it's also in the set B. I usually like to think of it in these terms, however. I think this is a useful thought. Your sets are disjoint if when you intersect them, there is nothing in common. A intersect B comes out as an empty set. Well, here's a couple quick exercises just thinking about disjointness, and then we'll look into example 11, which is meant to be kind of the challenge exercise in the notes for the day. First question really is just going back to the first section, sets of numbers. Recall Q refers to the set of rational numbers. I refers to the set of irrational numbers. And the question is, are they disjoint? Turns out, yeah, they're absolutely disjoint, but sometimes it pays to just say a little bit more here. If you just said yes for this as a problem on a homework, that would have been just fine. But to think through it, let's write out the set Q. We're going to use some set abstraction when we write it. The set Q is going to be the set of all fractions, P divided by Q, such that P is an element of the set of integers. We'll allow it to be positive, negative, or zero. And at the same time, Q is going to be an element of the set of non-negative integers. I'll write it out this way, greater than zero. We're just trying to avoid dividing by zero. So that's one way to write out the set Q. One way to write out the set I is to say it's a set of elements X in R. So these are real numbers such that X is not a rational number. They're irrational. That's just a shorthand for saying not rational. And now when we look at this definition, I is a set of all, oh, hang on, not in the set Q. X is irrational, should be written in this way, not an element of the set Q. So by the way these are written, we have rational numbers written as P over Q. The irrationals are the set of real numbers that are not in the set Q. So by definition, when we look into the intersection of these, the rational numbers intersect with the irrational numbers, comes out as the empty set. I'll write it this way, which then implies Q, I are disjoint as sets. Together, they make up the entire real number system, but there is no overlap whatsoever between these two different sets of numbers. And just to think about our set operations a little bit more, if we took the rationals and took that union with the irrationals, we get the entire real number line, the entire continuum of numbers. There are no holes or gaps. We get the reals. So these are not just disjoint, they are also forming a partition of the real number system as well. And we'll define partition in the next set or the next page. Well, any questions so far, folks, about thinking of disjointness? Okay. Part B is a little bit more abstract because we never said what the set A was. We just said, let it be some set. We're looking into the set complement, so there's got to be a larger universe where the set A and all other sets come from. We're asking if the set A and the complement of A are disjoint, but there's a pretty fast way to analyze that. you can write out the definitions of the complement of A. The complement of A is going to be the set of all elements X in the universe, whatever it happens to be. So not the union symbol, an actual uppercase U, such that X is not an element of the set A. So that's what the complement would look like. But then that means by this definition, if you took A, intersect it with the complement of A, this will come out as the empty set because there's nothing in common with either one of those sets. Just by the definition of the complement of the set A, there is zero overlap. So we can conclude here, therefore, A and the complement of A are disjoint. And this is true for any set A, even the empty set. By the definition, the empty set to intersect the empty set is still the empty set that has no elements in common because there's no element in either set. So this could be thought of as a formula. A set A and its complement are disjoint. That's a way to just define the complement in the very first place. Or maybe a faster, more routine problem, that'll be part C down below. But any thoughts or questions on part A or B so far? Oh, didn't mean to do that. Okay, let's try this out again. Question R, which sets are disjoint? And you might have already took a look at this, carefully use the eyeball it method, see which is which, and you have an answer ready to go. So if you answer questions just by saying these two sets and you called it a day, that'd be okay with this one. For a decent process, it's not a bad idea to think in these terms again. Take A intersect B. This is a set of elements common to both A and B at the same time. Let's see, 1, 4, 7, 10, 3, 5, 7. We have 7 in common. This is not the empty set. If it was the empty set, we'd say they are disjoint. So here we'll say the conclusion on this one is AB are not disjoint. By the way, you might have heard words mutually exclusive. That'd just be considered a synonym in this class for disjointness. If we do the same operation with, say, B in, hang on, let me go in order. Let's do A intersect C. A intersect C, well, let's look at this one. It has elements 2, 3. There are no 2, 3 elements in the set A, so automatically this is the empty set. And this implies the sets A and C are disjoint. Well, we found a disjoint set, but to complete the process, let's take B intersect C. B intersecting with C does have an element in common. Looks like it's the single element 3. Then this would imply B and C are not disjoint. So that's the rundown with disjointness. We get sets coming out as disjoint. We intersect them and end up with the empty set. Or thinking differently, the elements have nothing in common. Well, next thing we're going to take a look into is just taking a look into set membership and subset relationships, and then take a look into just a couple more additional topics. Any questions at the moment, folks, with what we've computed so far? Okay, here's that problem that we refer to as kind of a challenge question. These are tricky. These are the kind of problems where I have to take a look at these really carefully before I just write down a gut reaction kind of answer. Every one of these, in my opinion, are tricky kind of problems. There might be a problem like this on exam 1, but it might be a 5-point problem where it's just 1 point per part, maybe 5 parts, so that if you missed one, it's not very high stakes, really. Every one of these is a little bit tricky, but a good way to think about this is in terms of a nice analogy. So one analogy you might think of is X element of is kind of like referring to a file in your operating system. Is X a file inside a folder? when you write down a statement, say X subset or subset equals of, we're wondering if this whole thing is a folder, an entire subfolder or subdirectory in your file system. So if that analogy is helpful to you to think in terms of, it's really the same idea with sets. And this is a strong analogy to just programming in general. If you're looking into X being an element of something, it's like you have an object that's just an integer. If you're looking into the subset relationship, you're talking about a list of integers, not just one thing, it's an entire list, a whole new structure in the language itself. So looking at this one, this is asking if X is a subset, let me say that better. If the set X is a subset or equal to the set X, well, we can say that this one is true. Because if we look to the left, we're asking if every element in the set to the left is also an element in the set to the right. It's true, they turn out to be the same exact set, so we get a true statement on this one. Well, that's one down. Let's think about the next ones for just a moment. This one is asking, is the set X an element of the set X? Any volunteers for response on this one? Would you all say that this is true or that this one is false?
Would it be false because it's asking if the set X is in set X and not just X itself?
Yeah, absolutely. And that's a great way to think about this one. This one comes out as absolutely false. Here we have an element X. Over here, we have a set whose only element, let me bump that up. The only element is X itself. But we're asking, is a file, the entire set X, contained inside here? It's false because all that's inside here is X, not an entire file containing the set X itself. So kind of a tricky one to take a look into. So good call on that one. Let's contrast what happens with B against part C. It's using the element of operator as well. So we're wondering, is X, the thing inside, an element of the set here? Hang on, let me say this in a better way. I kind of confused myself. This one is asking if the set that contains X, that's a better way to say it, is an element of the set that contains X, but also a set containing X. That's kind of a hard way to say it. Let me write it out this way. Here, the only elements are X, but also the set that contains X. So we're asking, is there a set that contains X inside here? There is, it's right there by the red dot. So this one would evaluate to true automatically on this one. So this one came out as false. The only way the one above could have been true is if there's something like that contained inside the set in question. Again, it's good to kind of go slowly on these and absorb just what happened. Does that make sense to folks on why true on part C, but false on part B? Okay, now we're changing the operation here. We're going back to what we said on part A. It's now a subset relationship. Here, we're asking, is the set that contains X a subset of the set that contains elements 1, the only elements are 1, and the set X. Any volunteers for an answer on this one? Yeah, I agree with you on this one. This one comes out as false as well. Actually, this was pretty much the question that was posed on Tuesday's class at the very top of these notes. If one was in a set that contains something like 0, 1, 0, 5, but then a whole new set that has one inside itself. Same kind of issue down here on part D. So that was a great question that was posed. Here, when we look into this, we're asking, is the element X inside of here? But the only elements we have are just one, and like a whole new file that contains X, but that's not the same as X itself. Because of that, we would say false on this one. The only way part D would be true is if we wrote this. Is the set X a subset of 1, X, and the set that contains X? This is a weird looking set, but this has cardinality 3. The elements are not the same. Again, we're thinking of this as a file by analogy, and this is a folder that contains the same file X, but they're not the same structures. This would be true because of that object right there, but this one is false because X is not the same as the set that contains X. Sounds really pedantic, and to some degree it is until we start programming things. Then these kind of structures really do make a tremendous difference. But any questions at the moment, folks, on the rundown through these?
Yeah, I'm still confused on that because it looks like we're asking if the set of X is contained within that set. And it looks to me like the set is contained with that set. And
I see what you mean.
Yeah.
Kind of like what we did in part A, in other words.
Yeah.
I gotcha. Here's another kind of view on this one. Let me kind of partition this thought off. Another way to think about this is, let's say we flip it true, but we didn't do this. What would make it true? We can come back up here to make it look kind of like what happened in part A. Let's go like this. Suppose on the very left, we didn't say the set X, but what we said was the set that happens to contain the set X. Again, that sounds pretty pedantic, but in programming languages, that really matters how these structures are defined. This would be a subset of the set that contains 1 and the set X. Let's compare with what I wrote down with part A at the same time to really see it. This is true because the thing we're looking into is just the element inside the set, which is just X. It's also over here. This one's true. We ignore the curly braces, but focus on what's inside the outer brace. It's one element that contains the set X, and it's also here. That's what would make this statement true for a different kind of problem as well. Does that make sense for the difference between part D and this additional problem here?
Yes.
Awesome. Again, it's really hard to train your eyes to see this, especially when you're looking into this in the very first time. But one way to think about it is when we look into the subset relationship, we kind of flatten this out. We remove the curly brace and just look at what's inside. Let's see if it's inside here. And it gets a little bit much when you see this, but if you're looking into the subset relation on this one, we flatten out the statement by removing just the external braces and look at that object on the inside, the set X. We find it's also inside of there, so now we have a proper subset relationship. We use subset equals as kind of a default statement. You could have said a proper subset and it would made the same outcome of true. But thanks for asking about that one. Again, there's a lot of variety you can now kind of imagine, especially if you put more elements inside here. Nest the sets a little bit further, just like how folders can get nested further and further and further in a file operating system. But other questions or comments at the moment? Okay, well, let's move on to the next topic. Again, this one is kind of a challenge question. If it shows up on exam 1, the stakes aren't very high. It will be like a 5-point problem, and there'll be something like along the lines of 1 point each. So if we miss one of these, it's kind of easy to do. It's not going to like drop you down a whole bunch of percent in an exam setting. But here's the last additional 2 topics to take a look into. We vaguely mentioned partitions already when we said the real numbers can be partitioned into two different sets, the set of irrational numbers and the set of real numbers. But if we go to define partition itself, let's put a quick example above. Here's what the full technical definition will mean for a partition. Again, if you like analogies for operating systems, think of literally partitioning a hard drive. It's not a bad way to think about this. Imagine this is your hard drive, and our partition will look like this in a certain sense. But the nuts and bolts of the definition go this way. A partition of a set S, the set in question, is a set of sets. So that's already interesting. We require the sets to be non-empty in our definition for partition. So we don't want any weird vagueness going on. Every set has something to have a meaning in the partition. So all of these are sets themselves belonging to a set for some k value greater than or equal to 1. That says something already. We can have kind of a trivial partition where we just take one set itself to form its partition. But notice when we say partition of a set S, it'll be a set of sets, kind of looping back with what we were looking at up here, sets that contain sets and other elements. So if we tie back into the original comment we made, we can say a partition of the set of all real numbers, the number line interval notation negative infinity to positive infinity, is the rationals and the irrationals. So why is it a partition? Well, the first thing that has to happen in the partition is we fill out the entire original set completely. We take the union of all elements in that set, we get the original set S. The set S in this example will be the set of real numbers, and it is true that the set of real numbers is equal to rational numbers union irrational numbers. We take that for granted just as a quick example to think about a partition. So we take the union of everything inside the partition, we get the original set. That's not all. We need more going on with our partition. The major thing we want is zero overlap. In other words, disjointness makes a comeback in this definition. We have to have that our sets are disjoint. So for any index, these are where the index are coming from. They're between 1 and k integers. Any index I and j, where j and I are not equal, the sets ai and aj are disjoint, which just means ai intersect aj have no overlap. They are the empty set. This is true here. So we have part 1 checks out, the union works, and part 2 checks out. The irrationals intersect I said that backwards. The rational numbers, the fractions, intersect all of the irrational numbers, is indeed an empty set. They are disjoint. So that's what we want in our partition. We'll practice just a quick exercise on this topic here. But actually, the big thing that's going to come back when we get to later on in the course, beyond chapter 7, is partitions have a lot of roles in computer science. And we're going to take a look into this topic comes back in equivalence classes. So equivalence classes are a type of partition with extra relationships tied in at the same exact time. Here, because we're just introducing the topic and we'll come back to it later, all we're going to do is just write down partitions for a typical homework or an exam problem for sets like these. Usually they're going to be small sets so that we're not busy all day writing out the partition. But we want every possible partition of the set Y that contains just the 3 elements. First, any questions or comments with the definition? Okay, let's give this a try. first thing, the partition is going to be a set of sets. So when we go to start this out, here's what the answer is going to look like. Here is a partition. We're going to write down all of them. So for this partition, one way to think about it is you might want to have, say, a really ultra fine partition for some reason. You could do that by going back inside here and writing out a partition of A, B, C could just be a set that contains A set that contains B, the set that contains C. Let's double check if this is truly a partition. It has to do two things, recall. The union of the set A, B, and C is in fact the whole set A, B, and C, so it checks the box on this one. And every one of those sets we wrote down have to be disjoint. A intersect B, the set that contains A intersecting the set that contains B certainly has no overlap. And same for any pairwise intersection here. So they're all disjoint, and this will be one partition. We're writing down all partitions, so next, let's try and write out a different kind. If this is the finest partition possible for this set, what would be the opposite of it? That, I guess, blunt, the most blunt partition possible. What would you all say should go here? If it's not as ultra granular and fine as this, say the opposite, what would be the set inside?
The set ABC.
Yeah, absolutely. And that's kind of weird. Again, that's like the most trivial partition ever, but it's allowed in the definition. The number of sets that go on the inside, this would be 3 sets in this case, can in fact be 1. So if we decided to partition the set A, B, C into the set A, B, C, that counts. That's a true partition, just maybe not the world's most useful partition ever. It just satisfies the definition. Now there's all the partitions in the middle. Again, it's kind of a small problem because we didn't want to be stuck here writing these out all day, but we can find the middle ground. Maybe a set that contains just 2 elements and a set that contains 1 element, that would be a partition. So the next possible partition would be the set that goes, let's take both A and B. The next set, because we have to take the union of everything here, we get back to the original set Y. So just put that there to follow the color coding. We'll include the set C here, and that would be yet another partition. I mean, we could do this a couple more different ways, right? When we write down the first set that contains 2 elements, we're deciding what to exclude. I excluded C to start, so next, let's exclude B, kind of going in order. Next partition will be A, C, and then the set with 1 element containing B. Do that again, and we can exclude the set A. My first set with 2 elements will be B and C, and then the set A. And we're done. We have 5 partitions altogether. There's no middle or additional partition we can write because sets are kind of merciful in the sense that order doesn't matter. If you wrote this one as the set B, comma, then the set AC, that's the same set as this one here. So we have 5 partitions altogether, and our job is done on this one. Well, any last questions, folks, on getting through the definition of partitions? Just this fast example here. Okay, one question you might have had is, how can you know how many partitions you'll get before even getting started? That turns out to be kind of a complicated problem all in its own right, but it's something you could look up if you were so inclined, say doing a homework set. If you had a set of maybe 4 elements, you might wonder how many partitions are there? And so if you're curious, you could look into Bell's number, counts the number of partitions of a set with finite cardinality. That's a kind of a complicated formula, but Bell's number has been computed for sets, say 2, 3, 4, 5, and so on for large numbers. But if I had a set with, say, 81 elements, computing Bell's number, again, if you're curious, take a look into it. It's a pretty nasty looking formula. So that's why it's here just as a comment, but it's a pretty tempting comment because on the next problem, we're going to look into a power set. We have a really fast formula for that case. It just turns out Bell's number is pretty complicated for partitions. So here this will be the last topic of the day, the power set relationship. All these things are useful in some sense or form. The big idea with power set, I think my major application I can think of off the top of my head would be probability. Probability defines a function P, the probability set function. The domain of that function is a power set. The codomain is just numbers between 0 and 1 inclusive. What the power set is, written this way, is the set of all subsets of that set S. So every possible subset, we have to recall the empty set by its nature is also a subset of any set. And when we say subsets, we mean specifically this relationship, subset equals. That's really our default way of thinking of subset. If we meant proper subset, we have to always be very specific with that. So here's the good news when it comes to the power set relationship. If the cardinality of A is finite, fastest way to say it is it's equal to n. Now it means just an integer value. Then the cardinality of the power set of A, in other words, this means the number of all subsets in the original set A is going to be 2 to the size or to the power of the cardinality of A itself. That's kind of weird in a way. Let's think through that as we determine the power set of A, why that might be true. So again, kind of a small set, so we're not stuck here all day. But in our particular problem, the size of our set A is 4. And so this means the cardinality of the power set of A on this one will be 2 to the power 4. So we need to write down 16 different subsets to that original set A. Let's see if it really happens. So let's get started. Power set of the set A, by definition, is a set. So we started off with a set symbol, and now we're just thinking of every subset possible. I want to think in terms of kind of what we did with our partitions. We started with the most ultra fine granular partition possible. So I want to go in those kinds of lines of thought. The smallest subset I can think of, which is a subset of A, is the subset with cardinality 0. That's the empty set, and it's a true subset of the original set A. Then the next bigger sets are sets that contain 1 element, sometimes called singleton sets. And there's 4 of them altogether. They go 0, 1, 2, or hang on, 0, 1, and that pattern seemed right until I looked at the set. X and Y are the next elements, not 2 and 3. Now we can start taking elements, or excuse me, finding sets, subsets that have just exactly 2 elements. So let's try to do this in a particular order. If I'm looking into subsets of cardinality 2, I'll start off with a 0 and include a 1. Then move over, do the same thing for X and Y. 0 and X is another possibility. 0 and Y is another possibility. That's not all. We can move over to this element, take 1 and X, 1 and Y, and then finally, we can take X and Y. So those are all possible subsets that have cardinality exactly 2. We'll put in a comma, since we are listing all of the elements of the power set of A. They're all the potential subsets of the original set A. Now we want sets of size 3 altogether. So we're going with size 3. Maybe a different way to think of it is determine which one you're excluding. I'll start by excluding y. Then we'll have set 0, 1x. Let's exclude x next. The set would be 0, 1, y. Keep on going along those lines. Exclude 1. You have 0, x and y. Then exclude 0. You will have the set 1, xy. It's a subset of the original set, so it belongs to the power set. Well, let's think about this formula again. We're expecting 16 sets, and I believe we should be pretty close. But why does this formula work the way it does? It's because for every single set I had to make, it was a pairwise decision on every single element, just a yes or a no. Here, two possibilities, yes to 0 included, or no excluded. Another yes, no, another yes, no, and another yes, no. There's 2 possibilities and 4 different things we have to go through. That's 16 possible outcomes, 16 different states altogether on whether you're excluding or including the element. And there's one last set. You could say yes to every element, you're throwing them all in. That would have been the set A itself. A is certainly a subset of itself because we're doing that relationship, subset equals. So it works just as it works for the empty set. So these are the 2 extremes, the set with nothing. The set A is in fact a subset of itself, and everything in the middle. Let's count them off. Here's 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 different subsets. So that's kind of a nice formula to have in the background because, I mean, if you can imagine if this was 5, there's 32 sets altogether. I don't think I'll ever ask that on an exam. That's just busy work is what it would feel like. But then it would be really easy to miss one, so it's nice to have a formula that counts them for us. Well, that's what's going on in the world of sets. Any last questions at all, folks, before we finish off these notes? Okay, well, thanks for your hard work and participation on these notes. I feel like this section is pretty technical at first, but we revise these notes as we go. And the next sections we're looking into on the course page, they're going to be a little bit faster and more direct. 2.4, the major thing we're going to be talking about are sequences, Cartesian products, and just some side topics like vectors and matrices. And if you've taken linear algebra before, it's just a refresher on a couple topics there. 2.5 is going to get into issues of functions. But functions is really just defined in terms of sets, can be defined in terms of Cartesian products. So we're going to be revisiting this information as well in the section 2.5. Well, looks like this is all I have for folks today. I don't want to start a section in less than 2 minutes time, but have a great afternoon, folks. If you have any questions, I'll be happy to help out, but take care.
Thank you.
You betcha. Have a good one. Thanks.